This is Dr. D. Govardhan, Professor and Head, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing Macaulay's method for finding the slopes and deflection for simple supported beam in mechanics of solids. Mr. W. H. Macaulay devised a method, a continuous expressions for the bending moment as well as the slope in such a way that on doing integration, the constant of integration such as C1 and C2 which are obtained that are valid for all sections of the beam. Even though the law of bending moment varies from the section to section. When comparing this method with the integration method, this is one of the simplest method which is applicable for the beams which is subjected to not only for load which is acting that pointed at one point, it is also applicable for the beams which are subjected to number of point loads or the combination of simple supported beam, it is also a combination of uniformly distributed load as well as the point loads. So the following rules are observed while using Macaulay's method for finding the slopes as well as the deflection of the beams. The first method here is given rules. Always take origin on extreme left of the beam. That is, if the beam is there now, assume it is now simple supported beam is given. When we are considering for determining slope as well as the deflection, always consider here left hand side of the beam as a reference position. That is here a consider point nothing but from the here x from the left side we have to consider. Take clockwise movements as negative and left anti-clockwise movements as a positive. While calculating the slope as well as the deflections, it is convenient to use the values of kilonewtons for the force as well as the distance in meters. Consider simple supported beam of length L as shown in figure, carrying a point load at its center at C as shown in figure. For this beam, we have to determine the slope as well as the deflections by using Macaulay's method. Now take A as the origin, that is the left hand side of the beam as the reference position. Consider section X at a distance of X from A as shown in figure now. Now the moments Mx is equal to the moments at a distance of X. Here we are taking X. Now since the reactions are RA and RB, here first of all we have to determine, since it carries a point load at its center, RA is equal to RB, which is equal to W by 2 now. That is half of the load which is carrying now. This equation is only applicable when the simple supported beam is carrying point load at its center now. So here RA is equal to, we can take it as W by 2 now. Now we have to consider the moments at a point X now. So the moments you can take the forces which are acting toward the left hand side of the beam or right hand side beam, but the reference distance we have taken only from the left hand side of the beam according to the guidelines given by the Macaulay's method. So at a distance of x is equal to, assume mx, it is equal to RA into x now. Since the moment is acting in clockwise direction, so hence it is treated as a negative moment as per the rules now. Hence mx is equal to, we can take it as minus of wx by 2 now. The bending moment at any section in CB, because this is nothing but equation is applicable up to the up to the section C only now, because x is varying up to this C, there is no forces involving. Hence, this equation is applicable, that is mx is equal to minus half wx by 2 is applicable up to when x is equal to L by 2 now. But on moving toward the right hand side now, that is when you crosses C now, B and C, two forces are acting now. Hence, the bending moment, if you take x is equal to at this position now, that is behind the point C now, that is x. The bending moment is equal to at this point now. It is given by mx is equal to, this force is acting toward the left hand side, hence it is a negative, but the weight, that is which is acting at the center, it is acting in anti-clockwise directions, hence it is treated as positive. Hence, the modified equations, the bending moment at a point x, when x is lies between B and C according to this figure, is given by mx is equal to minus half wx by 2 plus w into x minus L by 2 now. Thus, the bending moment can be expressed for all the section of the beam which lies between A and B or x is equal to L now. But here, the bending moment can be expressed for all the section of the beam in a single equation as here this equation above mx is equal to minus wx by 2 plus wx minus L by 2. This equation is applicable when the reference point is lies between the B and C now. So if I put one dotted line here separation now, here now, this in the equation, this one now, that is the above equation can be written as mx is equal to minus of wx by 2 plus here I am putting some separator now, w into x minus L by 2 now. So these equations, when analyzing, the mx is equal to, if you take just the first term minus of wx by 2, this gives the bending moment equations for the force for the reference point, which is lies between C and A only. That is before the load which is acting at a C now. That is the W is acting now. But if you consider the point which lies between B and C, that is behind the load, we have to take addition of the content which is written behind the dotted line now. That is minus of wx by 2 plus wx minus L by 2. This is only single equations, but depending on your requirement, you can select the content which is applicable for determination of bending moment. That means first term is up to BC, AC. The second combination of first and second term, it is applicable for the entire length of the beam now. That is, when we are considering just between B and C, we have to consider the content which is written behind the dotted lines. Now rewriting these equations now, because mx is nothing but bending moment, the bending moment according to the integration method, we can write it ei into dy by dx square, that is the bending moment at any section is given by, which is equal to minus half wx by 2 plus w into x minus L by 2. So integrating this above the equations once again with respect to the x, we got ei into dy by dx is equal to minus half wx by 2, w is a constant, x integration is x square by 2 into by 2, hence it now becomes minus half wx square by 4 plus c1, that is known as the integration constant, plus the remaining values there now, w into x minus L by 2 whole square by 2 now. So here now this x minus L by 2 is treated as a single content as per the Macaulay's method now. So it is treated as single whole as a only x only now. So that is integration is x minus L by 2 whole square by here now 2 is written now. So integration, that integrating the same equation third once again with respect to the x once again, we got ei into y is equal to minus of w is a constant, x square integration is x cube by 3, already 4 is there in denominator, hence it now becomes 12 plus C1 integration is C1x. One more integration we are getting, that is second integration C2 plus W into XL by 2 cube divided by 3. Already 2 is there. Now hence it becomes 6 now. So in these equations, the third equation is representing the slope of the beam when it is subjected to a point at its center. When the considered point, if it is within the points A and C, it is applicable up to the dotted lines now, up to C1. When the point considered, which is beyond the point C, that is between B and C, this we have to consider the entire content of the equation now. That means whole length of the beam now. Similarly, the fourth equation is representing, that is the deflection of the beam up to C2. When we are considering the reference point is between A and C, and if the point is lies between B and C, we have to consider the entire equations now. Okay, from these equations now, applying some boundary conditions such that when x is equal to 0, that is at A, that is at this moment the deflection is treated as 0 now. That is x is equal to 0, that means y is equal to 0. At the same time, when x is equal to L, again y is equal to 0 now. So first we are taking x is equal to 0 in this equation, that means y is equal to 0, and substituting x is equal to 0 here, this content is equal to 0. Again the second one is also 0. Again C2 it is there now. When x is equal to 0 means 0 minus L by 2 whole cube by here 6 is there now. That is here from this equation, so when x is equal to 0, that nothing but here when you are putting, that is finally we are getting y is also equal to 0 now. In substituting these values in the equation number 1, we got C2 is equal to 0 values now. And when x is equal to L and again y is equal to 0. That means by using these two equations we got when x is equal to 0, that is y is equal to 0, that is representing C2 is also equal to 0 now. Now substitute these values x and y and C2 equal to 0 in equation number 4. We got EA into 0 is equal to minus half. Here on substituting these values, we got C1 is equal to, from these relations we got C1 is equal to minus half WL square by 16 now. So by using these equations we can put it now. That is the first one, we are putting x is equal to 0, y is equal to 0, that is representing C2 is equal to 0 now. The second one is when x is equal to L, we got C1. C1 is equal to minus half WL square by 16 now. So I am substituting the values of C1 in equation number 3. We got EI into dy by dx is equal to minus half WL square by 4 minus half WL square by 16. Here dotted lines plus W into x minus L by 2 whole square by 2 now. This is the equation number 5, which gives the slope of the beam at any sections. When we are considering the section between A and C, we have to consider the content which lies just before the dotted lines. For considering between B and C, that entire content of the equation 5 we have to consider for determination of slope, that is the dy by dx now. Thus for a maximum slope generally occurs at A, that is when x is equal to 0 in equation number 5 we got. From these relations, EI into IA is equal to, when x is equal to 0 and substituting, finally we got it is equal to, IA is equal to WL square by 16 EI and IA is equal to IB, both are equal because of its symmetry. Okay, substitute the values of C1 again in equation number 4 and C2 is equal to 0. We got these equations. It is known as deflection at any point within the beam now. But here now, before just dotted lines up to this red color, it is the equation is applicable for determination of slope between A and C, and that entire equation, that is including just behind the dotted lines, that representing the equation for the slope for the entire length of the beam, that is A to B now, that is beyond the point C now. So the maximum deflections generally occurs at the midpoint for the simple supported beam when it is subjected to a point load at its center. That means x is equal to L by 2, and substituting we got EI into YC is equal to, that is when x is equal to L2 means we require this slope at a deflection at a distance of C at a C, that is YC is equal to, and substituting minus of WL cube by 96 plus WL cube divided by 32. From this relation we got YC is equal to WL cube divided by 3EI. This is the expression for the determination of slope as well as the deflection for the simple supported beam carrying point load at its center by using Macaulay's method. This method is comparatively easy when comparing with the W integration method. Now, second expression now, simple supported beam with a eccentric point load using Macaulay's method now. Here consider a simple supported beam having supports at A and B at its end position and carrying a point load at C as shown in figure at a distance of A from end A and B from end B, it is at a distance of B as shown in figure now. Now, before considering this moments, that is the slope as well as the moments at any section, first it is required to determine the value of supports values at A and B in terms of its weight now. So, according to the equilibrium condition, so we are having three conditions. One is Fx is equal to 0, sigma Fi is equal to 0, and sigma at any point is equal to 0 required. Since there is no forces are acting in horizontal positions, hence the first equation is not applicable. The second equation is sigma y is equal to 0. That means sum of the forces acting in vertical direction should be equal to 0. From this relation we got to RA plus RB, it should be equal to W, it is equation number 1 now. Now moments at any point that is equal to 0, that means A or B now. If I take bending moment at B now, it is equal to MB is equal to, we can take it as RA into L, it is a clockwise directions, positive, assume here W is there now, anti-clockwise directions, W into B, it should be equal to 0 now. So from these relations, here we can take it as RA is equal to W into B divided by L now. RB is equal to WA into L, where A plus B is equal to length of the beam now. So after determining that is RA and RB, now consider a point X at a distance of X from the end A as shown in figure now. So assume we are considering here one point which is at a distance of X. Assume this point is also represented as a capital X now. So mx is equal to minus of, at A is equal to what is the value we are having? W into B by L, W into B by L into X. Here the minus sign is representing the moments are in clockwise directions. Now the bending moment at a point X, the point is lies between B and C now. It is similar to the previous expression. We got mx is equal to minus of WB by L into X plus W into, if I take this point is somewhere here now, this distance is equal to X minus A now. That is minus of WB by L into X plus W into X minus A, where this is known as here anti-clockwise movement, it is clockwise movements. According to the Macaulay method, the clockwise movements are treated as negative, anti-clockwise movements are positive now. So thus bending moment can be expressed for all the section of the beam by using only single equations. Now the modified equation of above, it can be written as now mx is equal to minus of WB by L into X. Here now dotted lines plus W into X minus A now. So the first part of the expression up to the dotted lines, it is represent the bending moment at a distance of X, that is X is equal to up to C, that is equal to only A now. X is equal to A now. So when the point is lies behind the point C now, that is behind the distance A with respect to the end A position now, we have to consider the two contents of 1 and 2 as shown in figure now. So now rewriting these equations now, since bending moment at any section is given by EI into dty by dx square, which is equal to minus of WB by L into x plus W into x minus CA now. So integrating the above equations with respect to the x, we got minus of WB into by L, x integration is x square by 2, here it is there, one integration constant C1 we are taking, plus W into x minus A, x minus A is treated as only single term now, hence its integration is x minus A whole square divided by 2 now. So it may be noted that that integration has been made as a whole, not the individual term in the expression now. Just integrating these equations once again with respect to the x, we got EI into y equal to minus half WB divided by 6L x cube plus C1x plus C2 plus W divided by 6 x minus C whole cube. Just I am giving once again now. In these equations, EI into dy by dx. dy by dx integration is y now. So WB by 2 by L is the constant now. X square integration is x cube by 3. 3 already 2 is there, it is equal now become 6 now. That means WB divided by 6L x cube now. Plus C1x now. C1 is the constant, that integration is equal to C1x, that x is adding. Plus CT is the another integration method, that is constant, that is second integration. Plus W by 2 x minus A whole square. X minus A is treated as only single term x. That the equation is x cube by 3, that is it can be equal to W by 6 x minus A whole cube now. That is already 2 is there, here become 3, earlier 2, 2 3 is 6, that's why we written 6 in this equations now. So by putting certain end conditions, we have to evaluate the integration constants C1 and C2. First by keeping when x is equal to 0, y is equal to 0 now. When x is equal to 0 means at end A position now, that is the slope at that point should be equal to 0. That means when x is equal to 0, y is equal to 0, and substituting the values in this equations we got, that is CT is also equal to 0 now. Now when x is equal to L, then y is equal to 0. By substituting these values in this equation, we got C1 values. First I am keeping now, substituting the values of x and y and CT equal to 0. In equation number 4, for evaluation of C1, we got EI into 0 equal to minus half W by 6L L cube, here plus C1 into L, that is x is equal to L we are putting, plus 0 plus W by 6 b to the power of 3 now. From these equations we got WB L square by 6 plus C1 into L plus WB cube divided by 6 equal to 0, or C1 L is equal to WB L square divided by 6 minus half WB cube by 6, which is equal to WB L minus B square divided by 6, or C1 is equal to WB by L into L square minus B square divided by 6 now. Now substitute the value of C1 in equation number 3, we got EI into dy by dx is equal to minus of WB by 2L x square plus WB by L, L minus B square divided by 6 plus W by 2 x minus A whole square. This is the required equation for determination of slope at any point on the section. And if the considered point is between A and C, we have to consider the content which lies between up to the dotted lines. If the point is lies beyond the point C now, where the load is acting, we have to consider the entire equations now. Now substitute the equation x is equal to 0. In fifth equation up to the dotted line only, we have that slope at A is equal to, that is x is equal to 0, and consider the equations up to 6. We got EA into IA is equal to minus half WB by 2L 0 square plus W by L, L square minus B square by 6 plus W by 2 into 0 minus A whole square. From these equations, IA is equal to W by L into WB by L into L square minus B square divided by 6 EI now. Since IA is equal to IB, here now, IA is equal to, we got to WA by L into L square minus C square divided by 6EI now. Okay, substitute the values of C1 again in equations now, and C2 is equal to 0. We got EI into Y is equal to minus of W by 6L into X cube plus W by L into L square minus B square by 6 into X plus W by 6 X minus A cube now. This is the required equation for determination of deflection at any section. The deflection at C, A and C, consider the equation up to the dotted lines, that is nothing but up to this point now. So EIY is equal to, just we got from this one now. Now, from this relations, I'm substituting this here now. Values of Y is given by, from this relation, so we got Y is equal to, this value it can be taken in denominator. Finally, we got on simplification, so Y is equal to W by X divided by 6LEI into L square minus B square minus X square. This method, this is the Macaulay method also used for cantilever beams for determination of slope and deflection at any point. Okay, problem number 5. Just based on Macaulay's method, we are taking one problem now. A horizontal steel girder having uniform cross section is 14 meters long and simple supported at its ends. It carries two constant loads as shown in figure. Calculate the deflection of the beam under the loads C and D now. Take Young's modulus is equal to 200 gigapascal and the length of the beam is equal to 160 into 10 to the power of 6. Sorry, I is equal to moment of inertia is equal to 160 into 10 to the power of 6 mm to the power of 4 now. So the given that in the problem is the length of the beam is given 14 meters. We are now converting all the dimensions into mm, because here now I is given in terms of mm to the power of 4 is given. That is 14 meters, 14 into 10 to the power of 3 mm now. So load at C is equal to, according to this figure, is given 12 kilonewtons, and the load at D, that is equal to W2, we are calling 8 kilonewtons. 8 kilonewtons means 8 into 10 to the power of 3 newtons. Similarly, 12 kilonewtons equal to 12 into 10 to the power of 3 newtons. Modulus of velocity is equal to 200 gigapascal, 200 into 10 to the power of 3 Newton per mm square. The moment of inertia is equal to 160 into 10 to the power of 6 mm to the power of 4 now. Now taking this movement at a point A, equating the same, because first of all we required RA and RB values now. So by using equilibrium conditions now, according to the equilibrium condition, the sum of the forces which are acting in the x direction is equal to 0. Sigma Fi is also equal to 0. Sigma F to any point you are taking MB or MB, it should be equal to 0 now. Since there is no horizontal forces are acting, hence this equation is not applicable for us. We have to consider only sigma Fi is equal to 0, sigma MB or MA is equal to 0. That is the moment at any point now. So by using these relations now, we got RA plus RB. The sum of the upward forces is equal to sum of the downward forces. From this relation, we got RA plus RB is equal to 12 plus 8, it is equal to 20 kilonewtons, or 20 into 10 to the power of 3 newtons now. Now the moments at a point A, when I am taking sigma A, RB tends to rotate the body in anti-clockwise directions, clockwise directions. That is, the sum of the moments which are acting in a clockwise direction should be equal to the sum of the moments in anti-clockwise directions. From this relation, we got to RB into 14, that is the moments in anti-clockwise directions equal to the 12 into 3, it is equal to clockwise directions, plus 8 into the distance called 3 plus 6.5, that is 9.5, which is equal to 112 now. So RA is equal to, we got to, from these relations RB is equal to, we got to 112 divided by 14 is equal to 8 kilo newtons, or 8 into 10 to the power of 3 newtons. But according to the relations already we determined RA plus RB is equal to 20. From these relations we got to RA is equal to 12 into 10 to the power of 3 or 12 kilo newtons. Taking A the origin now, that is left hand side of the beam now. First of all, consider one point according to the class methods. At a distance of x, we are taking now the modified equation is equal to here now EA into dy by dx square. That is the RA into x. First, when you are taking here now RA divided by x. This movement is in anti-clockwise directions. Hence, it is treated as a here negative. Here, when you are considering the point up to just beyond between C and D, just add one more here word now. That is 12 into 10 to the power of 3 into x minus 3 now. This distance is equal to x minus 3 because the first equation is applicable up to A and C now. When we are considering beyond C now, that nothing but we have to take one more point. If the point is lies at a distance between D and B now, like this, the additional point is we are getting 8 into 10 to the power of 3 into x minus 9.5 now. So just here this equation when we are integrating once again now, here first one is here x is there now, that is 12 into 10 to the power of 3, here x square by 2 plus C1 is the integration constant now, integration constant. So plus that is up to just here now when we are considering first integration up to the C only. Just behind this point it is there now. When the point is lies between C and D, we will take just one more constant up to this position. The third one is the behind now. Similarly, integrating the above equations once again now, we got EI into y is equal to, up to this one is the first integration method. That is the point is lies between A and C. If the lies between C and D, consider up to this point now. The remaining D and B nothing but entire equations now. When x is equal to 0, that means y is equal to 0. From this relation, we got c is also equal to 0. Then, substituting these values, we got from these relations, we got x is equal to 0 means y is equal to 0 or c is equal to 0. So, one integration constant, we got it now. The second one is when x is equal to, that is L, again y is equal to 0. By using these conditions, determine the values of integration constant C1 now. So by using these equations we got to, that is C1 is equal to, and doing the calculation we got to 193.2 into 10 to the power of 9 now. Substitute the values of C1 and C2 is equal to 0. The previous equations we got EI into y is equal to minus of 2 into 10 to the power of 3 x cube plus 193.2 into 10 to the power of 9 into x. So this is nothing but up to the between A and C. Beyond C and D, take up to additional one more content 2 into 10 to the power of 3 into x minus 3 whole cube plus between, if it is a point DB, one more content we have to take additionally, which is equal to 4 into 10 to the power of 3 into x minus 9.5 to the power of 3 divided by 3 now. The deflection here we required under load C, that is under W equal to 12 kilonewtons, as well as the 8 kilonewtons, that is x is equal to 3, one condition, and x is equal to 3 plus 6.5, it is equal to 9.5 we require now. So when you are putting this x is equal to 3, we got to the deflection is equal to 16.4 mm now. Similarly, at a point D means that x is equal to 3 plus 6.5 equal to 9.5. On substituting x is equal to 9.5 here in these equations, we got yd is equal to 20.9 mm now. So the Macaulay's method is comparatively easy when comparing with the double integration method for determination of slope as well as deflection when the beam is subjected to not only single, the several loads including eccentric load And this theorem is also applicable for cantilever as well as the simple supported beam. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.